All right, next we have Ken.
Hello. Cool. Hey guys, I'm Ken. I'm a software engineer at Bloomberg. And today I will be talking about a case study on building a real-time replication pipeline from an OLTP database to Apache Iceberg. And I just want to start it off just by giving a special thanks to people that aren't here today, and that wouldn't be possible without them. So most notably Anuj and Roy, team members that we all worked in the system together. Without them, this wouldn't be possible. To kick it off, just quickly go over the agenda of the presentation today. I'll kick it off with some motivations and challenges that kind of led us to build a real-time replication pipeline, and then some of the design goals that we had in mind for it. Then I'll go off to talk about the current system landscape and constraints that we're working with. Then go on the architecture, so existing architecture, and then what our new architecture is, and how we designed it with modularity and decoupling in mind. Afterwards, I'll discuss a little bit on how we maintain in production, what we have to monitor, and for operational visibility. And then I'll dive into the benefits of Iceberg that we observed, as well as some challenges along the road. And then at the end, it'll just be some final takeaways, and we'll open the floor for some questions. So some motivation design goals. To get some context, within a department at Bloomberg, we have a lot of ETL processes from a lot of different consumers that were running really heavy analytics and batch workloads against our operational database. And as you would assume, all this heavy ETL would have a cause for performance risk and contention. So with this, we kind of needed a system to decouple from our operational database, but still expose all this data for consumers to perform analytics. On top of this, data freshness is really critical. Downstream consumers that have these timely processes still need the timely data, right? And also designing this in mind, we also designed for extensibility as well as real-time use. So our system should be able to source from any different form of database and still work. And it should also align with the current industry standards of a lakehouse architecture. What were the current system landscapes and constraints that we were working with? So our OLTP database was in SQL Server, or still kind of is, and it served as the primary shared data source amongst different consumers. So we have these different teams in our department that would run these ETL workloads on this database, and again, with this really high read pressure during peak hours. And in addition to this, we also have ETL workloads that would rely on a separate replica database, where this replica database is populated from a custom CDC process. This custom CDC process relies on SQL Server's native CDC for table enablement, where we have these custom processes that would read from these change data capture tables and then push it over to the replica database. This is all in SQL Server as well. And with that, we weren't able to use SQL Server's native CDC for our new system. This is namely because the system already used the maximum number of capture instances, so which is 2. And this was to capture both row data changes as well as actual DDL changes within the table. And in addition to this, our custom process unfortunately deleted the capture changes after merging. So again, prevented reuse. Now let's quickly go over the existing architecture. On the left-hand side, we can see we have our OLTP database. We have these source tables that will go to these change data capture tables that I mentioned before. And on the right-hand side, our data warehouse, this is essentially a replica database. It has these jobs that will perform these sync and recovery processing, as well as a change puller that will pull the changes from our OLTP side, push it over to our replicated tables. And then after this, we have additional ETL workloads that would process and transform on these replicated tables, output it to another set, where then this final set would actually serve to our different applications and consumers. So for reporting, for analytics, and for business intelligence. Now, what does our new architecture look like for our new design with our replication pipeline? Instead of going to a SQL Server warehouse, it goes to Apache Iceberg. So similarly to before, we have our source tables, but now instead of actual change data capture tables, it goes to trigger-based event tables. Now, where this really differs is that in the change data capture tables, we would capture an entire row changed. So every single column in the replicated table we would capture. But now we only capture the primary key of what was changed and the operation. So if a row was inserted, updated, or deleted. And then going over to the replication pipeline, we, similar to before, we have this change poller. So this daemon that's, running and constantly checking if there's any changes in the event tables. If there is, it will format the actual row that was changed into some Debezium compliant message, push it to a Kafka queue, and then from there we have this Flink job that will stream the events from Kafka and eventually make its way to Apache Iceberg. And our Apache Iceberg tables live in S3 as object store, and it's also initially bootstrapped by an Apache Spark job. And now for this point, you can kind of see it's really similar to our previous diagram. We still have these jobs that are processing and doing transformations and still outputting to a set of process data tables. However, now instead of it being on shared SQL machines, it's all decoupled from our operational source and all within our data lakehouse. And as you can see in the previous diagram, our design is modular and decoupled. Although we have an in-house system, each component is decoupled and is compatible with open source standards. So for instance, the polling daemon that constantly pulls changes from the event tables, this could be swapped out with, say, Debezium. And for the Flink Iceberg sync portion of it, can also be swapped out with something like Kafka Connect. But in a high level, the design enables us to really iterate within the current constraints that we were given and still evolve as tooling becomes more available to us. And this can all be done without actually having to re-architect the entire system, entire pipeline. Now, with any CDC system, I think monitoring operational visibility is really important, right? One aspect that we do track is lag. So for instance, on the CDC daemon side of things, we publish metrics such as polling time and publish lag time. So given these metrics, we're really able to see when a change happens in a source table, we're able to see how long it will take for it to get to the actual destination Iceberg table. And on top of this, every replicated table also contains a default CDC field. And again, if you're familiar with Debezium or Kafka Connect, this field contains a really lot of important metadata. So for one, it contains the op field, so just to track the last operation that was taken on that row from the source table, and then the TS field just to see when that row was actually modified. And in addition to lag tracking, we also have scheduled data reconciliation. So this is really just a periodic job that compares an Iceberg snapshot against the replicated source. And this is really to ensure there's data consistency and there isn't too much data drift, if any. And although this job really was meant to be temporary, our cadence, we're likely gonna decrease the cadence as we gain more confidence in our system in terms of data consistency. And another thing we track that's pretty important is the S3 tendency and bucket metrics. So this is really just to see how our Iceberg tables scale in our S3 storage as there are more changes going on. And this is really essential for alerting, especially for our use case as a streaming use case. Now, Apache Iceberg has been kind of a foundation for this whole system. What were some of the benefits that we observed from using Iceberg? And one thing that's pretty, I think, well known is that Iceberg is natively ACID compliant operations. This allows us to have concurrent readers and writers, and the data will still be consistent amongst them. On top of that, in-place schema evolution allowed us to evolve a source table schema without any downtime within our system. And lastly, Iceberg's native merge on read semantics. We were really able to use this to optimize our writes using Flink without having a lot of load when we're writing. Now, what were some challenges that we experienced going on? I think, of course, it's gonna be challenges with any system, right? One thing is a pronounced small file problem with streaming rights. So this is both on the initial bootstrapping part with Spark, as well as writing it from Flink. In terms of Spark, it really depended on how many resources we really allocated for a given job, and that really limited on how many files that we would write to Iceberg. And then on Flink side of things, depending on how we configured our windowing, that made a drastic difference in terms of the amount of objects that we see in S3. And in terms of compaction strategy, one really important parameter, especially for compaction and rewriting data files, is the delete file threshold. So this is really to ensure that our delete files and our data files really get merged together when we do compact, and we can actually see storage gains from this. And lastly, another challenge was parity of data types between different technologies. So we're getting changes from some source database to Kafka to Flink, and then finally to Iceberg. And as you would assume, there's going to be a lot of data type considerations that we would have to really take note of. And one thing was SQL Server's datetime to Iceberg's timestamp, just getting those parity of granularity in terms of the actual seconds and milliseconds. And one other thing that we learned is, again, also frequent table maintenance and proper configuration was absolutely necessary. As you can see in the diagram on the right-hand side, on the y-axis, it's the amount of storage this Iceberg table is taken, and then on the x-axis, we see some dates, right? So within 3 days, we saw our Iceberg table nearly triple in size. And this wasn't because each day we actually saw that many changes for the given source table, right? But it was more so our initial maintenance configuration in terms of expirations. We only set it to expire snapshots that were 7 days, and with that, every subsequent write with Flink caused extreme ballooning of metadata. So that's really what we see in terms of storage increase right here. And in addition to this, some manual configuration for specific properties were pretty necessary. So most notably the commit retry properties. And this is primarily for when there's maintenance going on for the table and it might be taking a little longer. And then we also still need to replicate changes from Flink too. Now, some final takeaways. One big takeaway is really utilize existing open source tools and technologies when possible. If and when you are building your own though, do try to align it with open standards for compatibility and flexibility, just like our system. And really, it will give dividends in the future. And of course, we're still learning and expect to keep refining our usage and process as time goes on. And yeah, that concludes it. I don't know if you have any time for questions.
We have time for one question.
Thank you for your presentation. My question is, how do you sync schema from the online database to offline? So especially what schema evolution do you support for your online database? How do you ensure that they are always in sync?
Yeah, so because we're sending changes in a Debezium client format, if you look at like Debezium kind of messages, look at the format of it, it usually sends a before state and an after state in terms of the message. So that also includes schema as well. So then where we can use that Kafka message, and then in our Flink process, we know exactly what the new schema is, and we're able to compare that with our live Iceberg table. And then with that, we're able to do any safe, like quote unquote safe schema changes. There are some things that aren't supported in Iceberg as of right now. I think in V3 there's some support, but yeah.
Sure. I see you have both Spark and Flink.
Yes.
Why can't you use one?
Yeah. So we're mainly using Spark. I think with the parity of technologies, it's kind of difficult. There are a lot of things because Spark really is mature in terms of handling Iceberg. So that's why we use Spark for initial bootstrapping. That was the main priority. Yeah.
All right. Thank you, Ken.
Awesome. Thank you.